Good morning, dear students. In today's class, we are going to learn about losses in optical fiber. Already in the last class, we have learned about the first losses. The first one is absorption losses and their types. So in today's class, we are going to see the remaining two losses. One is scattering losses in optical fiber and another one is bending loss in optical fiber. So first let us see the scattering loss in optical fiber. So here the scattering losses in fiber exist due to various factors. One is microscopic variation density of the fiber material, compositional fluctuation, another one is structure inhomogeneities, another defects in fiber. Again, this scattering losses exist in optical fiber because of microscopic variation in the material density and composition. As we know, here we are using a glass material. So as a glass is composed of randomly connected network of molecules and several oxides. For example, let us consider silicon oxide, germanium oxide, or phosphorus pentoxide. So these are the major cause of compositional structure fluctuation. So here because of these effects we will occur a scattering losses. So the scattering losses can be classified into two types. One is linear scattering and another one is non-linear scattering. Again, this linear scattering is divided into two types. One is Rayleigh scattering and another one is Mie scattering. Again, this non-linear scattering is divided into stimulated Brownian scattering and stimulated Raman scattering. So due to this scattering results in attenuation in the form of radiation, as the scattered light may not continue to satisfy the total internal reflection in the fiber core. So we have to this attenuation less signal, we have to make a total internal reflection, right? So due to this attenuation or due to this scattering attenuation, so it will produce attenuation in the form of radiation, as the scattered light may not continue to satisfy the total internal reflection in the fiber. Now let us see the linear scattering. So this linear scattering causes or transfers linearly the optical power in one propagation mode to different mode. So these losses will occur in leaky mode or radiation mode. So it will continue to propagate within the core of the fiber and radiated out from all the fiber. So all the linear process, there is no change of frequency on this scattering. So let us see the Rayleigh scattering. So this is the Rayleigh scattering. So this Rayleigh scattering of light is due to small localized. Here we have some scattering light, right? So this Rayleigh scattering light is due to small localized change in the refractive index of the core and cladding material. So here we have two causes during the manufacturing of process. Already manufacturing of fiber process. So already we have seen this fiber, what are the causes of fiber on manufacturing. So first one is due to slight fluctuation in mixing of ingredients and the random change. So mixing these ingredients, here we will have some random change. Because of this or impossible to eliminate completely, right? So first thing is due to slight fluctuation mixing of ingredients. So we are mixing some silicon oxide, germanium oxide, phosphorus pentoxide, like that. So mixing of these ingredients, there will be have some random changes. So these random changes are impossible to eliminate completely. So the second causes is slight change in density as the silica cools and solidifies. So on the manufacturing process of fiber, we have to cool the fiber, right? So at the case, a slight change in the density, it will produces some scattering, right? So when the light ray strikes as zones, it gets scattered in all directions. So when the light ray strikes, so it will be scattered in all direction. So the amount of scatter depends upon the size of discontinuity compared with the wavelength of light. So the shortest wavelength suffers most scattering. So shortest wavelength refers to high frequency, that will suffer most scattering. So the scattering losses for single component glass is given by alpha scattering. So attenuation can be represented in terms of alpha. So alpha scat represent the scattering is equal to 8 pi cube divided by 3 lambda power 4 n square minus 1 the whole square kb tf bt Neppers. Neppers is the unit of attenuation. So we all know that, right? So where here the value of n, here we are representing the n, right? So here the value of n is equal to refractive index, and Kb is the Boltzmann constant, beta T, here we have the value beta T. Beta T is the isothermal compressibility of material, and Tf is the temperature at which density fluctuation are frozen into the glasses as it is solidifies. That is nothing but a fictive temperature. So let us see what is fictive temperature. Fictive temperature is defined as the temperature at which the glass can reach a state of thermal equilibrium. So it is closely related to annual temperature, right? So fictive temperature is nothing but at which the temperature at which glass can reach a state of equilibrium. So at which state the glass can reach the equilibrium state, that temperature represents the fictive temperature, right? So next we can represent the scattering attenuation in the form of another equation. So that is alpha scattering is equal to 8 pi cube divided by 3 lambda power 4 n power 8 p square kb tf beta t. So the unit is Neppers. So here the changes is there we have n square minus 1 the whole square. It can be replaced by n power 8 and a p square. So this p represents the photoelastic coefficient, right? So the scattering loss of multiple component glasses are given by alpha scattering is equal to 8 pi cube divided by 3 lambda power 4 delta n square the whole square into delta v. So here the delta n square is the mean square refractive index fluctuation, and delta v is the volume of fiber. In multimode, fibers have higher dopant concentration and greater compositional fluctuation. Therefore, the overall loss in the fiber are more compared to the single mode fiber. Next one is mice scattering. So let us see, sorry, next one is mice scattering. So let us see what do you mean by mice scattering. So Mie scattering means when the scattering in homogeneity size is greater than the wavelength lambda divided by 10, the scattered intensity which has an angular dependence can be very large. So the scattered created by such inhomogeneities is mainly for in the forward direction, and it is called as Mie scattering. So how we can reduce this inhomogeneities means by removing imperfection due to the glass manufacturing process. So we have to remove the imperfections so that we can reduce this type of scattering, and we have to carefully control the while manufacturing. We have to take much care to avoid this type of scattering, again by increasing the fiber guidance, by increasing the refractive index difference. So by this we can possibly we can reduce the Mie scattering, right? So how we can reduce this inhomogeneities means by removing imperfection due to the glass manufacturing process. So next we can see the non-linear scattering. So here optical waveguides do not always behave as completely linear channels. So here increase in optical output power is directly proportional to the input of optical power. So nonlinear effect occurs in the case of scattering causes disproportionate attenuation, usually at a high optical power level. So it causes the optical power from one mode to be transferred in either the forward or a backward direction to the same or other modes at different frequency. So here we have two types of nonlinear scattering. One is stimulated Brownian scattering and another one is stimulated Raman scattering. So let us see what do you mean by stimulated Brownian scattering. So it is the modulation of light through thermal molecular vibration within the fiber. So this Brownian scattering occurs when we are modulating the light through the fiber. Due to the thermal molecular vibration, the light gets scattered. So this effect is called stimulated beryllium scattering. So the scattered lights appears at upper and lower sideband, which are separated from the incident light by the modulation frequency. Here the frequency shift is a maximum in backward direction, reducing zero in forward direction, making this stimulated beryllium scattering mainly in backward process. So this stimulated beryllium scattering is otherwise known as SBS. So S stands for stimulated and B stands for beryllium and S stands for scattering. So once again, so where this stimulated beryllium scattering occurs means when we are the modulation of light through the thermal molecular vibration within the fiber. So at this place, if the light gets scattered, so the scattered light appears as upper and lower side bands, which are separated from the incident light by the modulation frequency. So the frequency shift is a maximum in backward direction, so very less in the forward direction. So mainly this SBS will flow in the backward direction. So let us assume the polarization state of the transmitter light is not maintained properly. So therefore, the threshold power PB. So here, due to beryllium scattering, the power in this here we are in the suffix we have the capital B. So this B stands for beryllium and P stands for power. So the threshold power PB is given by PB is equal to 4.4 into 10 the power minus 3 d square lambda square alpha dB. So alpha dB is nothing but the attenuation into V. So here this D refers to, here we have the value D, right? So this D refers to fiber core diameter. So this diameter in the range of micrometer. Again, lambda is, we all know lambda is the operating wavelength and the wavelength unit is in micrometer. The wavelength should be in the micrometer range, and this alpha dB is the fiber attenuation in dB per kilometer, where this V, here we have the value V. So V is the source bandwidth in gigahertz. So now let us see stimulated Raman scattering. So it is otherwise known as SRS. So this S stands for stimulated, R stands for Raman, and this S stands for scattering. So this SRS is stimulated with high frequency optical photon is generated in the scattering process. So by using this SRS, we can stimulate it with high frequency optical photon is generated in this scattering process. So this XRS can occurs in both forward and backward direction in optical fiber. So we know this stimulated beryllium scattering always travel in the, due to scattering, the light wave travels into the backward direction. Here in Raman scattering, this scattering occurs and it will flows in forward and backward direction in the optical fiber. Therefore, the threshold power is given as. So here we are representing the Raman scattering. So here we are in the suffix we are represented R. So the value of PR is equal to 5.9 into 10 to the power minus 2 d square lambda square alpha dB watts. So how we can reduce this non-linear scattering means it can be avoided by the use of suitable optical signal level, that is working below the threshold of optical power. So how we can, we have to reduce this type of scattering, then only we can transmit the signal without loss, right? So how we can reduce the non-linear scattering means, so by choosing a suitable optical signal level, that is we have to choose the optical, that is we have to choose the threshold optical power below the, sorry, we have to choose the power below the threshold optical power, so that we can avoid these type of losses. Next we can see the bending losses. So bending losses are due to curvature and losses caused by an abrupt change in the radius of the curvature are referred to be bending losses. Here we have the sharp bend of the fiber, right? So the sharp bend of the fiber causes significant radiative losses, and there is also a possibility of mechanical failure. Right? So these type of losses are represented as bending loss. As this core bends in the normal, right? Here the core is bending. It will follow it, and here the ray signal will follow it, and the ray will now find itself on a wrong side, right, of the critical angle and will escape. Right. So we know the waves should travel in a total internal reflection, right? So instant wave should be reflected back and then it will be traveling. So due to this bending, so this light waves will be escaping from this core. So this type of losses is called bending losses. So this bending losses is divided into two types. One is micro bending and another one is macro bending. Now let us see what do you mean by macro bending. So this is macroscopic bending. So it occurs when the radius of the curvature that are large compared with the fiber diameter. Example, when a fiber cable turns at the corner, right? So this figure shows the macroscopic bending. So here the change in the spectral attenuation caused by macro bending is difficult from micro bending. So usually there is no peaks. So here in this my micro bending, there is no peaks and troughs, because in a micro bending, no light is coupled back into the core from the cladding, and can happen in the case of the micro bending. So in this micro bending, the signals can be coupled, but here no signal can be coupled in the macro bending. So no light is coupled back into the core from the cladding as it happened in the case of micro bending. So this type of bending causes some losses. That type of losses is represented as macro bending. So this macro bending losses are caused by the large scale bending of fiber. So here the fiber is large scale, right? So these type of bending of fiber will causes a macro bending. So these losses are eliminated when the bends are straightened. So by straightening this, we can reduce these losses. These losses can be minimized by not exceeding the long term bend radii. So here this macro bends may be reduced by designing fiber with large refractive index difference. So while designing this macro bending, we have to have the value, refractive index of the value should be very large, and operating at the shorter wavelength is possible, right? So the first thing, how we can reduce this macro bending means designing the fiber with large relative refractive index difference, and here the operating at the shortest wavelength is possible. So this is called as macro bending. Now let us see microscopic bending. So here the losses are due to small bending or distortions, right? So here we have a small bending, or we can represent this as a distortion. So this small micro bending is not visible, right? So this is the glass fiber. In the glass core can be covered with cladding. Cladding can be covered with buffer. So it was not visible, right? So this losses are due to this temperature related, tensile related, or crush related. So due to this losses occur, and this micro bends are due to small scale fluctuation in the radius of the curvature of the fiber axis. So this situation arises when the fibers are cooperated in the cables. So how we can minimize this micro bending means by introducing compressible jacket over the fiber. So by um, introducing the compressible jacket over the fiber, we can reduce these type of losses. Then already we have in this, let us summarize the losses. So here we have of losses. One is absorption losses, another one is this scattering losses, and another one is bending losses. So in this today's class we have learned about the scattering losses and the bending losses. Again, this core and cladding losses, so another one losses are there. So this core and cladding losses have different refractive indexes because they are having different composition. So due to different composition, we have to choose different refractive indexes, so we can avoid this core and cladding losses. So that's all about today's class. Thank you, students.